Welcome back to the fourth lesson in the OpenLI training series. In this chapter, we are going to start looking at OpenLI itself for the first time. I will begin by describing each of the components of the OpenLI system and explaining their role. I'm also going to talk about the typical hardware requirements and deployment strategies for each component, so you can get an idea of what equipment you would need to buy and where to place it within your network. Before we begin, it may be worthwhile to remind ourselves what OpenLI is and how it is different from conventional LI systems. As I mentioned in the first chapter, OpenLI is an open source alternative that is designed to allow smaller network operators to meet their lawful interception obligations without having to spend a large amount of money. The software itself runs on standard off-the-shelf x86 server hardware with Linux as the underlying operating system. OpenLI is compliant with the key ETSI standards for LI, including those for IP, voice over IP, and mobile data interceptions. The codebase is actively developed and maintained, and we have had multiple successful deployments by network operators, mostly here in New Zealand, but we are also assisting with deployments in other countries as well. The OpenLI software consists of three primary components, which each perform distinct roles within the OpenLI system. These are the provisioner, the collectors, and the mediator, each of which I will now describe in more detail. The first component is the provisioner, which implements the administration function which you may remember from the first chapter of this training material. The provisioner acts as the central controller for the entire OpenLI system and will be your primary point of interaction with OpenLI once you have it deployed and running. Authorized personnel within your organization will use the provisioner to stop and start intercepts in response to requests from LEAs, as well as to configure or modify other aspects of the intercept system as a whole. All of the configuration actions can be performed through a REST API using a standard set of HTTP request methods. Typically, OpenLI users will be starting and stopping intercepts very infrequently, so the provisioner component will not be required to do any work most of the time. This means that you can easily run the provisioner component within a small VM or container, or even run it on the same host as the other OpenLI components. The provisioner will need to be able to communicate with all of your other deployed components, as they will be relying on the provisioner to tell them what to do. However, for security reasons, the provisioner should not be reachable from outside of your network. Otherwise, malicious actors could use your provisioner to interfere with ongoing intercepts, or even to use the provisioner to start intercepts and have that intercepted traffic forwarded to them. Even on-network access to the provisioner should be strictly limited to a very small number of approved personnel only. And to assist with this, the OpenLI REST API supports enforcing authentication via either API keys or by using HTTP digest auth headers. Moving on to the collectors now. This is the component that actually performs the interception of network traffic and therefore has the highest computational load. The collectors are somewhat complex because they have to perform a number of tasks simultaneously: listening for new intercept instructions from the provisioner, capturing packets from the collection interfaces, interpreting AAA traffic to follow user sessions and their corresponding assigned IP addresses, determining which packets should be intercepted, encoding those packets as ETSI compliant IRIs and CCs, and finally forwarding those encoded records onto the mediator. Now, as you can see, that's quite a lot of work, so let's take a closer look at some of these tasks in more detail. Obviously, packet capture plays a significant role in the operations of a collector. It is important that you choose an appropriate capture method for the traffic load that you expect the collector to have to handle. Hopefully, the previous lesson has been quite helpful in this regard. Please note that a collector may support packet capture on multiple interfaces simultaneously, and it may make sense for you to deliver different types of traffic to a collector on separate interfaces, such as IP traffic on one interface and AAA traffic on another. While certain packet capture methods such as DPDK are capable of handling large volumes of traffic, you should still try to make an effort to prevent any extraneous traffic from reaching the collector software, as every packet captured still requires CPU cycles to process, even if it is not going to be intercepted. The collectors themselves support the use of BPF filters that can be used to discard certain types of packets before they reach the collection threads. But this is not particularly efficient. If you can, it would be better to avoid mirroring traffic to the collectors that is never going to be intercepted. But this may not always be easy to configure or control, depending on how you are doing the mirroring. Another of the tasks that a collector will perform is to track user sessions and IPs. OpenLI supports several different session management, or AAA, protocols, but Radius is the protocol that most OpenLI users have been using in conjunction with their collectors. The way that this works is reasonably simple. The operators must pre-configure, via the provisioner, the IP address and ports being used by their Radius servers. From then on, any traffic observed by the collector matching one of the Radius servers will be redirected to a separate thread, which parses the Radius messages and uses them to maintain a table of all active users and the IP addresses that have been assigned to them. This information is used by the collectors to then determine whether any given packet belongs to a user who is an active intercept target, and therefore whether the packet should be intercepted. Using that radius state, the collectors can now make decisions about whether a captured packet should be intercepted or not. Again, the overall approach is reasonably simple. For each captured packet, the collector will examine the source and destination addresses in the IP header. If either of those addresses matches an address that has been assigned to a user who is an intercept target, then we can intercept the packet. If not, then the packet can be safely ignored by the OpenLI collector. Of course, for this approach to work, the collector must see all radius traffic that relates to users who are sending or receiving the IP traffic that is being captured by the collector. Without the corresponding radius, the collector will be unable to associate the correct IP address with an intercept target, and therefore will fail to intercept that target's traffic. Once a packet has been intercepted by the OpenLI collector, it then needs to be encoded to comply with the ETSI mandated format for CC and IRI records. The standards specify the encoding formats using ASN.1 and expect the records to be encoded using basic encoding rules. Different types of intercepts will require slightly different encodings, so voice over IP intercepts are encoded differently to IP data intercepts, which are different again to mobile data intercepts. Because of the intricacies of the encoding rules, this encoding can be a computationally expensive task, although we have recently managed to make some enhancements to our encoding approach to save a lot of time. To support all of the specific requirements of the ETSI standards, we ended up writing our own library for encoding and decoding the records, which is called libwander, and we have also released that library as open source software. The ETSI standards also introduce some other complications that we have to account for in our encoding process. Two that stand out as worth mentioning are the requirement for ETSI records to have consistent and strictly ordered sequence numbers, which can be quite tricky to achieve in a highly parallel environment, as well as the requirement for IRIs and CCs for the same intercept to have consistent identifiers, even if they are generated via separate code paths. The last collector role that I'll talk about here is the forwarding of the encoded records to the mediators. Again, we need to be careful about delivering records in their correct sequential order, so this thread may need to reorder records prior to forwarding if the use of multiple encoding threads has meant that they are received out of order. The forwarder is also responsible for the temporary buffering of encoded records if the mediator happens to be unreachable for any reason. OpenLI supports the use of RabbitMQ to buffer records, which allows you to make use of the collector's disk for buffering if required. Otherwise, the collector will buffer directly into memory. This will buy some time for the mediator to return, but will eventually exhaust the memory of the collector host if the problem is not promptly resolved. Of course, the more memory that your collector has, then the longer it will be able to wait for the mediator to return. One key design feature of OpenLI is that you can distribute multiple collector instances throughout your network, rather than relying on one single large collector to handle all of your traffic. We typically suggest that you deploy one collector instance alongside each major customer aggregation point in your core network, such as a BNG or whatever equivalent you happen to use. The most important thing to remember is that your collectors need to receive a mirror of any corresponding AAA traffic for the users whose traffic is going to be seen by that collector. otherwise the collector cannot track sessions and user IP assignments properly. Similarly, for voice over IP interception, both the SIP and RTP traffic for a call must be seen by the same collector for an interception to be successful. Because the collectors have to do so much work, you'll need to think more carefully about the hardware that you'll be running them on. If your hardware is under-specced for the amount of traffic that you need the collector to intercept, then you're going to risk dropping packets and your intercepts may be incomplete, which will in turn make the LEAs very unhappy. It can be a tricky balancing act, so take some time to consider what your likely maximum intercept throughput might be, given your prior experiences with intercept requests and the bandwidth that you offer to individual customers. The first thing you'll need to decide on is whether to run your collector on a bare metal server or whether you are going to run it within a VM. Bare metal will likely give you the best raw packet capture performance, but virtualization has come a long way and we have plenty of OpenLI users that are happily running their collectors within virtual environments. The decision will most likely depend on what will be easiest for you to integrate and manage within your existing network. The main rule to remember when choosing hardware for OpenLI collectors is that more CPU cores is generally better, as many of the tasks that the collector performs can be done for multiple packets in parallel. Past experience suggests that an OpenLI collector would need around 16 CPU cores to be able to intercept 10 gigabits per second of network traffic. 8 of those cores would be used for packet capture, 4 cores for encoding, and the remaining 4 would handle the other tasks such as sequencing, forwarding, and session tracking. Collectors with smaller workloads could reduce the number of cores for capture and encoding. 4 capture cores and 2 encoding cores can easily intercept 1 or 2 gigabits per second of traffic. For traffic rates larger than a gigabit per second, we strongly recommend that each collector use a high-performance network interface card to perform the raw packet capture. The card should be a model that supports either DPDK or XDP, and many 10 gigabit per second cards should be compatible with either of these technologies. However, it pays to double check before you buy, just in case. Ideally, the card would have at least 2 interfaces, one that you will use for packet capture, and the other that you will use for forwarding intercepted traffic to the mediator. Your collector should also have a second card, preferably with at least 4 interfaces that you can use for out-of-band management, communication with the provisioner, and for capturing other lower rate traffic streams, such as your AAA or voice traffic. These interfaces do not need to be particularly high capacity. 1 gigabit per second should suffice in most use cases. Generally speaking, a collector does not need a lot of memory, especially if you intend to use RabbitMQ for record buffering when the mediator becomes unavailable. 16 gigabytes of RAM is the amount that I would recommend, but you may wish to add more if you're going to rely on in-memory buffering. In terms of disk, an OpenLI collector has no special requirements other than ensuring that you have enough spare space for buffering. An old-fashioned spinning disk should be fine, but feel free to put in an SSD if you prefer. Because raw customer traffic is presented to network interfaces on a collector, you will need to take extra care with your security policy for the collectors. Fortunately, once deployed, there should be no need for anyone or anything that is not an OpenLI provisioner or mediator to interact with or log into a collector. This means that your security policy should end up being relatively simple. Specifically, no collector should be visible or reachable from outside of your core network, and only the person responsible for maintaining and upgrading the collector should have the ability to log into it at all. The third and final component in the OpenLI system is the mediator. The mediator essentially serves a single purpose, which is to implement the handovers to the LEAs. To do so, a mediator must perform several concurrent tasks. Firstly, the mediator must maintain a list of all active intercepts and which LEA has requested each of them. This information is provided directly by the provisioner. Secondly, the mediator must establish and maintain TCP sessions for both the HI2 and HI3 handovers to each of the LEAs that you must provide intercept capabilities to. These sessions must be up continuously so that the LEAs can be aware of whether your LI system is functional or not. Thirdly, the mediator must perform its core role, which is to receive encoded etc records from the collectors and then forward them on to the corresponding LEA using the appropriate handover. If the handover is unable to accept records for some reason, the mediator must buffer the records until the handover is available again. Let's delve a little more into the specifics of the handovers. The TCP sessions for the handovers will usually be established within an encrypted tunnel, such as an IPsec tunnel. This will need to be configured before you start up your mediator, and your LEA should provide you with the necessary details for configuring the tunnel, such as the endpoint addresses. As I mentioned earlier, it is expected that the handover sessions will remain continuously active, even when you have no active intercepts. The mediator will regularly send keep alive messages over the handovers to allow the LEA end to know that your system is still active and functional. One final thing to note is that the handover connections are always initiated by your mediator connecting out to the LEA. The LEA will never need to try to connect to you. What this means is that although your mediator will need to be able to make outgoing connections to the LEAs via the public internet, you can safely firewall any connection attempts to the mediator that come from outside of your core network, which once again makes creating a security plan relatively straightforward. As with the collector and provisioner, once the mediator is deployed and started, there should be little need for anyone to log into the mediator aside from regular maintenance and upgrades. So once again, SSH access can be very strictly limited on the mediator to just the person who would perform those tasks. In terms of hardware, the biggest concerns for a mediator deployment are the amount of memory and the networking capacity. Unlike the collectors, the mediators do not currently support disk-back buffering, so if a handover fails during an active intercept, then the mediator will be relying solely on memory for buffering until the handover returns. For this reason, I would recommend a minimum of 16 gigabytes of RAM for a mediator, and ideally you want as much as you can reasonably afford. For the networking, your mediator will need to be capable of receiving and simultaneously forwarding your expected peak rate of intercepted traffic. There's no point in deploying collectors that can capture an intercept at 10 gigabits per second if your mediator can only receive and forward at 1 gigabit per second. So in that case, your mediator will need at least one 10 gigabit per second interface for receiving records from the collectors and another 10 gigabit per second interface for running the handovers. A third lower capacity interface will also be needed for out-of-band management and communication with the provisioner. By comparison, the CPU is less important for the mediator component. There are some parallel elements in the mediator software, but the core functionality right now occurs within a single main thread. I would still ensure that your mediator has a reasonable number of cores available to it, but 8 CPU cores should be more than enough for most OpenLI deployments. You should also be fine to deploy your mediator within a virtual or containerized environment if you wish. Most OpenLI deployments will only have a single mediator, as LEAs tend to prefer that an operator presents them with only one set of handovers. The OpenLI software does support the use of multiple mediators to distribute workload if needed, but you should definitely check that your LEAs can accept the delivery of intercepts from multiple mediation functions before adding additional mediators to your planned deployment. So to reinforce what we've learned, we can use this diagram to visualize a typical OpenLI deployment and the relationships between the three components. You can see the provisioner on the left-hand side, which receives instructions from the network operator via our REST API. These instructions are then interpreted and sent downstream to the appropriate collectors or mediators so that they know what to do with the packets or records that they observe. The collectors are distributed throughout the core network, one alongside each of the BNGs that we have. The BNGs are mirroring network traffic and the relevant session management protocols into their corresponding collector. Packets that belong to an active intercept target, as instructed by the provisioner, are intercepted by the collectors, encoded as valid ETSI IRIs and CCs, and then passed on to the mediator. The ETSI records are then forwarded on to the appropriate LEA by the mediator using the correct handover, again as dictated by the instructions received from the provisioner. All in all, it's a very simple and elegant system, and by now you should already have a fairly good idea of how you might go about integrating OpenLI into your network. Finally, we can visualize the OpenLI architecture from a security perspective, where we see that all of the OpenLI components are strictly contained within the operator domain. There are only 2 points of contact with the outside world. The first is the REST API that is used to configure the provisioner, which should be authenticated, restricted to on-net access only, and available to a very small set of personnel. The other is the handover interfaces, which should only make outbound connections over a pre-configured encrypted tunnel directly to the LEMF. Most importantly, all access to your OpenLI infrastructure from the public domain can and should be blocked by your regular Edge firewall, as external access is not required at any point. In fact, aside from regular maintenance, there should be no need for anybody to log into your OpenLI components at all once they're up and running. I will note here that there are a small number of jurisdictions where LEAs can issue interception requests electronically and will then expect that the intercept will be automatically configured on the deployed LI system, bypassing any manual process that involves the operator. In that case, there would need to be an extra communication channel for HI1 that receives requests from the LEAs and talks directly to the provisioner REST API to enact the intercept. This obviously introduces some extra security concerns, although the strict use of encrypted tunnels and IP-based firewalling should alleviate these problems for the most part. And that brings us to the end of this lesson. By now you should be very familiar with the three OpenLI components and what their roles are in a typical OpenLI deployment. You should also have some thoughts about where you might want to deploy the components within your network, which will lead nicely into our next lesson, where I will walk you through how to install the OpenLI software and keep it up to date. Hope to see you again soon.